Here's a problem where we start with the pulleys. So we have what we want to do is we want to figure out how many times this cord or this belt is wrapped around this pulley system or this drum or sheave or whichever one you want to call it. So first of all, let's write down our givens. So first, let's take a look, and we have our given. We know that at one end we have, let's call this T2 is equal to 100 newtons. That's in one end we have the pulley or the belt is tensioned to 100 newtons. On the other end, and what I'm going to do is also with this notation, this 1 means it's going to be greater than 2. So we have 20 e to the 3 newtons. And then on this side, if you further on down, we have a coefficient, we're going to call that mu, is equal to 0.3. What we're trying to find is the number of times, so let's call that n. The number of times can be decimal place. So first we want to do, if we want to visualize this, we have to understand what's going on. So we draw a sheave or a pulley or a drum in 2D, and we put a little thing like that. And then what we're going to do is we're just going to say that's one end, and it wraps around. So if anybody has ever climbed before, you can see the power of friction interacting right here. So that, with that, the more times you wrap it, the better off this is going to be for you to force multiply these two forces. So let's take a look. And when we cut this, we're going to cut it here, and we're going to put this in tension. We're going to say that this is T1, and we're going to cut this here, and this is going to be T2. So we have this belt, and again, if it was frictionless, these two would be the same. But in reality, there is some friction there, and you can get that in the machinery's handbook. This mu, you can get this by knowing the two different types of materials. So let's look at the solution. Well, let's start to look at the solution. So the main equation for this is T1 over T2 is equal to the exponent theta times mu. So with that, what we can do is we rearrange this, and we'll know right from the get-go that this T1 is known, this T2 is known, and also this mu is unknown. So the only unknown is going to be theta. And then we can rearrange the theta to figure out what our n is. So let's do that. We can do that in multiple steps. One thing is we can take the natural log of one side, and what I'm going to do is I'm going to put theta times mu on this, and then I can put the natural log of T1 over T2. And we can find a number for this, but let's keep going. So we have this theta now is equal to mu. We have this 1 over mu ln T1 over T2. So we can get, now we have, once we know that, our theta now becomes known. And then what we want to do is we want to find the n. So the n, we want to turn that into kind of revolutions. So we know that 1 rev is equal to 2 pi. And we multiply this times theta to get our value. And if we put in the numbers, you'll notice that it actually takes 2.18, I believe, or 81. Let's do this real quick. So I think it's 18 revs. 18 revs. So that's how we would figure this out. And that would be what this n value would be. So it takes twice around and then some to actually produce that. So you can actually force multiply almost, you can go up 4 orders of magnitude just by wrapping this belt around this sheave, this pulley, this drum to force multiply, which is fantastic force multiplier. So with that said, that's how you would solve this problem. And good luck, and I will see you soon.